Welcome. This podcast is going to look at ceramics, one of the big categories of materials within material science, and what the thermal properties of ceramics are. I'm Miss Mikesell. I'm one of the material science teachers at Eagle Crest High School, and I hope this podcast is helpful. So, what is a ceramic? Simply stated, the definition of a ceramic is a solid material that is not a metal, a plastic, or derived from plants or animals. So, ceramics are a vast category of materials, and interestingly, we define them by what they are not. So, refractories are heat resistant materials that are used for lining the high temperature furnaces and reactors. A great example of a refractory surface is the inside of an airplane engine. The combustion chamber of an airplane engine temperature often exceeds 900 Celsius or 1,650 degrees Fahrenheit. What's crazy about that is that's higher than the melting point of the aluminum alloy that is used um, to make the blades within the engine. So, how can you have something that has a melting point below the temperature at which the engine operates? Wouldn't the blades of the engine melt? And it is a ceramic coating on the blade, as well as cooling channels cut into the blade that allow it to operate. The blades actually operate in an environment several hundred degrees hotter than the melting point of the nickel alloy. But because of the cooling mechanisms, the metal is never above its melting point, even though the environment is. And so, one of the things we're going to look at is the tremendous low thermal conductivity of ceramics, which makes them really good for the linings of furnaces, reactors, and engines. Abrasives are ceramics that are used to smooth, polish, and grind materials. So, sandpaper is a common ceramic abrasive. And as the video discussed earlier, the fact that ceramics are incredibly hard is what makes them excellent abrasives. Ceramics and glasses are the hardest type of any solid material. Many ceramics are used as abrasives in cutting, grinding, and polishing, and that is because their hardness is really high. Unlike metals, it's really difficult for dislocations to move through the atomic lattice. And that is because of the ordered bonding between the atoms in ceramics. So let's look at the bonding that occurs in ceramics. Ceramic materials can often contain both ionic or covalent bonds. If we remember from our previous semester, covalent is when electrons are shared, whereas ionic is when the electrons are transferred from one atom to another. And the bond force determines the properties of the ceramic material. When two atoms are far apart, there's an attractive force, and that increases as they get closer. When the atoms get so close that their electron cloud starts to overlap, there's a repulsive force that prevents them from getting any closer together, as shown in the diagram on the left. So the stronger the bond force is between the atoms in a ceramic, the higher your elastic modulus will be, the higher the melting point of the ceramic will be, and it will affect the thermal conductivity, the ability to transmit heat energy through the material, and make it very low. So if we look at the mechanical properties of ceramics, we can see that our standard metals, aluminum, copper, iron, and nickel, tin and zinc fall here, and our ceramic material, alumina, magnesium oxide, silicon nitride, and silicon carbide are above it in terms of where they land on the stress strain curve, their Young's modulus value. However, if we look at glass and glass ceramics, we can see that they're in a similar place in terms of stiffness to many of the metals that we've looked at previously. However, they are not as strong as other ceramics. So in general, the properties of ceramics are that they are hard and strong, but very brittle. They have high melting points. They have a high heat capacity and a low heat conductance. They're corrosion resistant, and they can be either electrically insulating, conducting, or superconducting, and either magnetic or non-magnetic. Ceramic materials can be either crystalline or amorphous. Rapid cooling of ceramics favors amorphous, since time isn't allowed for the crystal structure and the orderly arrangement to form. And if a ceramic material is amorphous, that's going to determine the properties that we see. And if a ceramic material is amorphous, they tend to have fractures occur in this conchoidal pattern. So amorphous ceramic materials tend to be brittle, and they break or fracture in a way that doesn't follow any natural planes of separation, creating these conchoidal fractures. And that is due to the lack of a structured crystal atomic lattice. So, thermal conductivity in a ceramic measures how a material spreads heat within itself. So we're looking at how heat energy can move through the material when we're looking at thermal conductivity. And if you remember in class, we did a demonstration where we put equal amounts of heat energy on an aluminum rod, right? An aluminum rod and an alumina rod. An aluminum rod is metal, alumina is a ceramic material, and we had placed various crayons at each of these numbered spots on those rods to see the rate at which the crayons melted and fell off over time. And if you remember in our demo, all of the crayons, all the way back to position 1, fell off the aluminum rod because metals conduct heat very well. They're great conductors. Whereas the first crayon at position 6 on the aluminum rod never fell off, even after crayon number 1 fell off. And that is because ceramics are very poor conductors of heat energy. They have a low thermal conductivity, which makes them a great insulating material used for things like refractories, furnaces, or engines. So the coefficient of thermal expansion is the rate at which a material expands with an increase in temperature. Most materials swell with the application of heat because energy is causing the atoms to move more rapidly, stretching their bonds. Ceramics generally have a low coefficient due to their strong bonds. That makes them more stable across wider temperature ranges. If we look at the coefficient of thermal expansion, we can see various materials and their coefficient of thermal expansion, or how much they will expand or swell as heat energy is added to them. And you can see comparison to a couple of metals that we've previously studied, steel and aluminum. So steel and aluminum swell significantly compared to ceramics with the same amount of heat energy input. Thermal shock resistance is the ability to withstand dramatic and sharp temperature changes. Ceramics and glasses generally have a low thermal conductivity. So what that means is when they're exposed to a rapid change in temperature, the specimen is heated or cooled at the surface, but because the thermal conductivity is not good, it doesn't change the center of the solid. Therefore, the surface of the material expands or contracts and is restrained by the center, which is unchanged. This is why ceramics, if exposed to wide, fast, quick changes in temperature, often become brittle and break. So if we look at an example of that, if a hot specimen is dropped into cold water, then the conduction of heat is going to cool the outer material, but because ceramics have a low thermal conductivity, the inner material is going to stay warmer. And therefore, the surface is going to be held in the tension. And tensile stress at the surface is relieved through cracking, through the brittle nature of the ceramic. So to test thermal shock resistance, you simply take a ceramic and heat it to progressively higher temperatures and then drop it into cold water And we're looking at the maximum temperature that the ceramic can survive before it starts to become brittle and eventually break, right? So spark plugs in your car can suffer thermal shock when the engine is started. And we can see with a spark plug, if we heat it up to 180 degrees and drop it into cold water, we see no signs of thermal shock. But at 200 degrees, we're starting to see that tension being relieved through cracking at the surface. And if we have a 220-degree drop in temperature, the spark plug is brittle and breaks into many pieces. And so thermal shock resistance would tell us that that a spark plug can handle a change in temperature up to 180 degrees Celsius. After that, we're going to see damage to the part. So calculating thermal shock resistance is the following equation. We're going to take and find the thermal shock index, and we do that by taking the tensile strength times the thermal conductivity and dividing it by the thermal expansion coefficient and the Young's modulus value. So let's think about these variables and how they would affect thermal shock index. The coefficient of thermal expansion, right? The lower the coefficient, the smaller the dimensional changes in the material as heat are exposed. So therefore, it's going to make thermal shock smaller, because if we don't have the material expand or contract as much with changes in temperature, we'll have less tension forces. Thermal conductivity is when the temperature gradient of the material is affected by thermal conductivity. The higher the thermal conductivity in the material, you can transfer heat more quickly and reduce the temperature difference. So for ceramic materials that have a low thermal conductivity, because that temperature difference cannot be reduced as quickly, they are more prone to thermal shock. The Young's modulus value is the modulus of elasticity. How much strain is allowed before the stress reaches a level that causes fracture? And then finally, the fracture stress. If strength is higher, then larger strains are possible. Fracture stress is high for a given material if there's few flaws in the material and they are very small. So we've talked about direct and indirect relationships multiple times, but I'm just going to remind us that if we're looking at a direct relationship on a graph, as the x value increases, the y value would increase. So when we have an increase in the x value, we see a corresponding increase in the y value. And so we often symbolize that with, as the x variable goes up, the y variable goes up as well at a proportional rate. And an indirect relationship is the opposite. Graphically, when the x value is low, the y value is high. And as the x value increases, the y value is decreasing, right? So let's look at this graph and figure out what's the relationship between the pore volume fraction and thermal conductivity. Hopefully you told me that you see an indirect relationship here. As the pore volume fraction increases, the thermal conductivity of the material is decreasing. Could you take a second and extrapolate from the measured experimental data trend? So let's look at these points here in the trend line that are right along these circular points. What's the thermal conductivity if the pore volume fraction was 20%? So again, I'm going to follow this line of best fit to here. At 20%, if the pore volume fraction was 20%, then the thermal conductivity would be estimated to be somewhere around 0.46, 0.47, and that would be in the units of watt meters per Kelvin. So why does a light bulb burn out over time? A light bulb burns out over time because of sublimation. The metal tungsten filament is changing from a solid directly into a gas as it's being used over time. You can actually see that sublimation occurring because when it becomes tungsten becomes a gas, it darkens the outer glass bulb of the light bulb, creating that kind of sooty shaded appearance. When we removed the glass bulb, though, in the lab that we did with light bulbs, we saw that the light bulb burnt out very quickly in a matter of seconds compared to the hundreds of hours they can last for in normal use when the bulb is there. And the reason for that is oxidation. Oxidation is a chemical reaction that takes place when a substance comes into contact with oxygen or another oxidizing substance. So, our tungsten metal filament, which is at a really high temperature as energy is running through it, was directly oxidizing with the oxygen that it was now exposed to with the glass bulb removed. The glass bulb normally contains inert gases like argon inside, sometimes krypton, although it's much more expensive, to prevent oxidation. So, since direct oxidation was occurring, that metal material, the tungsten, is becoming ceramic. And ceramics are poor conductors of electricity, they're insulators. So, that circuit was getting more and more diminished over time. And eventually, the ceramic becomes so brittle that it either breaks, burning out the light bulb, or the circuit ends because the ceramic is so insulating it stops conducting electricity through it. I hope this podcast was helpful. Have a great day.